Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about another important probability distribution, the beta distribution. Okay, let's begin. My plan is the following. First, I'm going to show you the expression of the PDF, the probability density function for a random variable with a beta distribution. Okay. Next, I'm going to, with your help, well, we're going to be doing it together, right? We're going to be finding the expected value for this kind of random variable. Okay. And finally, what we're going to be doing at the end of this video is doing an example where this probability distribution is applied. Okay, first, as I said, let me show you the expression that defines the probability density function for a random variable with a beta distribution. As you can see, this formula, this PDF, is defined, fully defined by two parameters. Okay, we need two numbers to know exactly which member of this distribution family we're talking about. Both alpha and beta have to be positive, and as you can see here, the constant that makes this expression, this PDF, a legit PDF, meaning that the integral from negative infinity to infinity of f of y is going to be equal to 1, right? We know that's one of the properties of a legit PDF. So this constant here is the one that is going to help us satisfy that restriction. Okay? But I know that at first it looks kind of scary, but it shouldn't be for us, right? In another video, we have already talked about the gamma function. So we know that when you evaluate the gamma function at particular values, alpha and beta, what you're going to have here is just a number, a constant. And as I said, this constant is going to be such that when you find the integral, in this case the only region where the PDF is non-zero is from 0 to 1. So when you integrate from 0 to 1, this expression here, you will end up with a beautiful 1. Okay. So before we move on, okay, take a look at that expression. Let's rewrite it here. So PDF, so f of y is given by this. We know that that constant we have in front will be defined by the gamma function. So it's going to be alpha plus beta. Those are the parameters that we have here, alpha plus beta. And then we have the product of the gamma function evaluated only at alpha times the gamma function evaluated at beta times, and then we have y to the alpha minus 1 power, and we have 1 minus y to the beta minus 1 power. Oops. And we know that we are going to be using that expression for y's that live between 0 and 1. Okay? and it's going to be 0 elsewhere. Okay, so example, because I want you to see that you have dealt with this kind of PDF before and you didn't know it. Okay, so let's see what happens if you evaluate when alpha equals 1 and beta equals 1. That's one of the members of the beta distribution family. Right? Example, let's set alpha equal to 1. Let us set beta equal to 1 as well. Let's see what happens. So in that case, let me copy paste this. So we have 1 plus 1, so gamma at 2, right? Divided by the gamma function evaluated at 1, the gamma function evaluated at 1, 1 minus 1, 1 minus 1 here as well, right? And it's going to be, just to be, very explicit, f of y will be 0 elsewhere. Let's do it here as well. Okay. But now, take a look at this one, the part where the PDF is different from 0 in that interval, 0 to 1. If you simplify, remember that in another video, when we talked about gamma distributions, we also talked about this guy, right? Actually, we devoted an entire video to introducing the gamma function, right? And what we said is one of the properties of the gamma function is that if you evaluate it at an integer, generic integer, n, so gamma at n equals n minus 1 factorial if you have an integer. So gamma at 2 would be the same as 1 factorial, and 1 factorial is 1. By the way, we also showed, just using the definition of the gamma function, that gamma evaluated at 2 is 1. So both ways, right? We showed that gamma at 2 equals 1. So again, we showed that gamma evaluated, the gamma function evaluated at 1 is 1. Another way of seeing this would be, okay, gamma at 1 must be, 0 factorial. Okay, which is 1. So we end up with 1 times 1, so that's just a beautiful 1. So we might as well just write it down like this. This is going to be y to the 0 power. So this is just 1. 1 minus y to the 0 power, that's just 1. So 1 times 1, that's just 1. Okay? And then it's going to be 0 elsewhere. Right? So what I wanted you to see is that this is the PDF between the non-zero part of the PDF between 0 and 1. It's just 1 there, right? So this guy is a uniform distribution, right? And we have talked about uniform distributions before, right? So again, you have dealt with members of the beta distribution family without knowing it. The uniform distribution is a particular case of the beta distribution. Now, just let me say something more. If you plan on taking a course in Bayesian statistics, beta distributions play a very important role in defining something that we in Bayesian statistics call prior distributions. Okay. Anyway, Let's go back to our lecture notes. Now let me show you graphical representations of other members of the beta distribution family. So this one here, when alpha equals 1 and beta equals 1, as we said, is uniform, a continuous uniform distribution in 0, 1, right? And the blue one is when alpha equals 2 and beta equals 2, you get something like this. And if alpha equals 8 and beta equals 2, you get something like this, right? Okay, so if we go back to the agenda that we had at the beginning, I said that our next goal would be finding the expected value for these guys, for a formula for the expected value for random variables with beta distribution. So let's take a look at two of these members of the beta distribution family. So for instance, if you are dealing with a uniform, right, meaning a beta 1, 1, clearly the center of that PDF must be 0.5, right? And if you take a look at the blue one, when alpha equals 2 and beta equals 2, looks something like this, upside down parabola, right? It looks like the center should be also close to 0.5, or maybe it's exactly 0.5, right? Okay, anyway, let's try and find a formula for the expected value of a generic beta distribution with parameters alpha and beta. Okay, so expected value of y. It turns out, and that formula is there in our lecture notes as well, that the expected value of beta distribution with parameters alpha and beta is alpha divided by alpha plus beta. Let's see if that makes sense. So we said, for instance, that in the case of a beta distribution with parameters alpha equals 1 and beta equals 1, we have the uniform distribution, and then it makes sense that the center of that distribution was going to be 0.5 or 1/2, right? So if alpha equals 1, we have 1 divided by 1 plus 1, 1/2. So that formula makes sense. Okay, we'll see if we can show, or how we can show this in general for any beta distribution with parameters alpha and beta. So proof that the expected value for a beta distribution with parameters alpha and beta is alpha divided by alpha plus beta. Proof. So how about we start with the definition of the expected value in the case of a continuous random variable. So by definition, the expected value of y, if y is a continuous random variable, would be the integral from negative infinity, need a minus here, minus, that's better, oh, minus infinity, so from negative infinity to infinity of y times the PDF of your random variable y, right? Okay. So we know that in this particular case, let's be super specific, we will break down that integral into three integrals. One, from negative infinity to 0 of y times 0, right? Because you know, outside the interval 0, 1, we have a 0 there, right? Okay, so that's one. The other one will be the integral from 0 to 1. Okay, so let me copy paste this, and now let me go up here and copy paste this expression. That's the PDF, the expression for the PDF in that interval 0, 1 for a generic beta probability distribution. Okay, plus, and then we have another integral similar to this one, but the you know, the interval, the lower and upper limit will be different. Okay, you guys agree? So we're being super specific. Okay, but we realize, right, that the only one that matters is the second integral, this one here. Okay, now let's try and rewrite it. First, y times y to the alpha minus 1 power, that could be re-expressed as y to the alpha plus 1 minus 1 power, right? Now, this guy, we know, right, we have experience with gamma functions. This is just a constant. So let's pull it out, okay? Let's place that outside our integral, okay? So let me copy paste this and rearrange. So as I said, let me pull that one out. We get to do that because integrals are linear, right? And let me rewrite this as alpha plus 1 minus 1. Agreed? Okay, no problem, right? Okay, so next, remember that when we talked about the deriving the formula for the expected value for a gamma distribution, we used the following trick. We completed inside the integral the expression of a legit PDF. Okay, and since and this one, sorry, this should be between 0 and 1, right? That's the only part that we should have here. Sorry about that. Okay. So as I was saying, so what we did back then was completing inside the integral the expression of a legit PDF, because we know that the integral of a legit PDF, right, is going to be 1, right, if you integrate it over the entire region where the PDF is different from 0, right? Okay, so let's do the same here. Okay, so see what we have. So we have y to the alpha plus 1 minus 1 times 1 minus y to the beta minus 1. Okay, compare that to the expression that we had for the generic random variable with a beta distribution. So we have y to the something minus 1 times 1 minus y to another something beta minus 1, right? So in this case, y to the something, instead of being alpha, is alpha plus 1. The beta seems to be, the same. Okay? But so all we have to do is, instead of in this part where the constant is defined, instead of using alpha, let's use alpha plus 1. Alpha plus 1. Beta is the same, right? So if we had this gamma evaluated at alpha plus 1 plus beta divided by gamma evaluated at alpha plus 1 times gamma evaluated at beta, that guy would be the PDF of a beta random variable with parameters, instead of alpha plus 1 and beta. Over 0, 1, well, we know that that integral is going to be 1, right? So let's do that. Let's complete that integral. Okay, so we said inside the constant that we need, and let me borrow this one. I'll copy paste this and modify accordingly. So instead of alpha plus beta, we want alpha plus 1. Right? And we want alpha plus 1, right? And again, what we have inside that integral, this expression here, is the PDF of a beta random variable with parameters alpha plus 1 and beta. And we're integrating over 0, 1, so that integral is 1. But since we are multiplying by this and dividing by that, well, this is a constant. So in order to, don't do any, in order for us to be on the legal side of the math, we have to, just if we're multiplying by a constant, let's divide by the same constant, and that's basically multiplying by a 1, and then that's a legit move in math, right? So let me multiply by the reciprocal. So here we're dividing by this. Let me multiply by that. We're multiplying by this. Let me divide by that. But now, as you can see, this is just, multiplying by a 1, no problem. But then this integral here, we have completed the expression of a beta, right? So in the end, on the next line, what we will have is just these guys times 1. Because that integral, even if it looks scary, is just a beautiful 1. Okay? Okay. So now, remember that we devoted an entire video lecture to talk about properties of the gamma, about the gamma function, and we derived a property, we showed a property of the gamma function. So the property that we showed was that if you evaluate, right, the gamma function, right, at alpha plus 1, that's the same as alpha times gamma evaluated at alpha, right? Remember, that's one of the properties of the gamma function. Okay, so that is going to help us to simplify this expression. So as I said, gamma at alpha plus 1 will be the same as alpha times gamma, the gamma function evaluated at alpha. So, and now this one here, to make it super clear, we could rewrite as alpha plus beta plus 1, right? Alpha plus beta plus 1. It's the same, right? Okay. So let me simplify this using properties of gamma function. This one here, gamma evaluated at alpha plus 1 is the same as alpha times the gamma function evaluated at alpha, right? We showed that. Now this one here is gamma evaluated at something plus 1, so it's going to be the something times gamma evaluated at the something minus 1, right? Oh, right? Makes sense? So in this case we have alpha plus beta plus 1, right? So it would be just alpha plus beta, gamma evaluated at alpha plus beta. Okay, so let me do that. Right? So this guy will cancel out with this guy, this guy, this guy, this guy, with this guy, right? So in the end, the only thing that we're going to have is alpha divided by alpha plus beta. Make sense? And that's exactly what we wanted to show, right? So that's why it was important to talk about those properties of the gamma function. Well, that property, by property of gamma function. Okay, so we're done with that part. We have shown that the expected value of a beta distribution is alpha divided by alpha plus beta. And again, what I wanted you to see is that the idea behind that proof was the same as the proof to derive the expected value for a gamma distribution. Basic idea is completing inside that integral the expression of a legit probability density function. Okay? Okay. Now let me find the exercise that I would like to do with you. Okay, let's go back to our lecture notes. I think the one I want is here. Yeah, that's the one I want. So let's try and talk about our last item in our agenda. Let's try and do exercise 4.131 together. Okay. So in this case, it turns out that a good mathematical, a good probabilistic model for these measurement errors is given by a particular member of the beta distribution family. A beta distribution with parameters alpha equals to 1 and beta equals to 2. Okay? Okay. Okay. So then, once we have identified the member of the beta distribution family that we're talking about, we will use it to compute that probability that the measurement error is less than 0.5 microseconds, I believe, would be the units. Yeah, microseconds. So, and then once we have that, they want us to find the mean, meaning the expected value, and the standard deviation. We know that the standard deviation is just the square root of the variance. By the way, there's a formula for the variance of the of our beta distribution. Let me go back to the slide where we have those, right? I think it's here. So see, we have already shown this. So if we want the variance, and we have already realized that we're dealing with beta distribution, you could find the variance like this using that formula and then just take the square root. Okay, no need to do all the math. Okay, so that's what we're going to be doing, right? Just using these formulas. We have already shown this one. If you have time later today, try and show this, the formula for the variance. Okay, anyway, let's go back to our problem. Okay, so exercise 4.131, let's do it. Let me open a new one here. So exercise 4.131. Okay, so we have that alpha equals 1 and beta is equal to 2. Okay, so let me borrow, sorry, not this, let me borrow the expression for a generic beta distribution. Okay, so let's plug in. So it would be 1 plus 2, 1, 2, we have a 1, we have a 2 here, right? And we know that it's going to be 0 elsewhere. Outside the 0, 1 interval, then that's just going to be 0, right? So let me now just talk about the non-zero part. This is the part that matters to us. So what we have is gamma at 3 divided by gamma at 1 times gamma at 2. Okay, so again, remember that we said that for integers, right, greater than 1, what we have is that the gamma function evaluated at n equals n minus 1 factorial, right? Okay, so gamma at 3 would be the same as 2 factorial, right? But 2 factorial is just 2. Now gamma at 1, we have already shown that gamma at 1 is just 1, right? And even at 1, the formula for the gamma at n equals n minus 1 factorial, it also works for that one, because you know, 0 factorial is just 1 by definition. Anyway, so gamma at 1 is just 1. Gamma at 2 would be 1 factorial, so it's just 1. So in the end, this constant turns into just a beautiful 2. Y to the 0 power, that's just a 1. And then we have 1 minus y to the power of 1. So it's just 1 minus y, right? Okay. So we have identified the member of the beta distribution family that we're going to be using. Let's go back to the statement of the problem. What we want now is the probability that the measurement error is less than 0.5. Okay? So let's do A. We want the probability that the random variable y is less, right? Less than 0.5. And just a comment, right? Not that it matters in this case, but it says strictly less. But we know that even if we compute it less than or equal, in the case of continuous random variables, that is not going to make a difference. Okay? Okay, so now if you want to find that, we know that what we need to do is integrate the PDF over the region of interest. So in this case, it's going to be from 0 to 0.5 of this guy. That's a PDF with respect to y. Okay? Now let's do it step by step, carefully. We could break down that integral into two integrals, right? So that's the same as 2 times 1 dy. So let me do that integral here, dy. Okay. Then we're going to have a second integral. And then that's going to be minus, right? Minus 2 times y. Okay? So it would be minus 2 times y with respect to y, right? No problem. Okay, so we know that by the linearity of integrals we get to pull out those constants. So it's just, we pull out, let me pull out that 2 here. Let me pull out that 2 there. Okay? Okay, so now easy. Those integrals are really easy, right? The integral with respect to y of 1 is just y, right? So it's going to be 2 times y, and then we're going to evaluate that guy at 0. We're going to evaluate it at 0.5 as well. Then we have 2 times this guy, the integral of y with respect to y is just, y squared divided by 2. So let's write that down. Y squared divided by 2. We're going to evaluate, same here, 0, 0.5. Okay, no problem. Okay, so then this is going to be 2 times 0.5, right, minus 2 times 0. So it's just going to be 2 times 0.5. Let me write that down. Then we're going to have 2 that multiplies, a 2 that divides. Those guys are going to cancel out. So we're just going to have y squared evaluated at 0.5 minus y squared divided evaluated at 0, right? So in the end, we only have 0.5 squared, right? Easy. Let's just, do the math. No problem. It's so easy in this case that we don't need a calculator. 2 times 0.5, that's 1. This is 0.5, or 1/2 squared, that's 1/4, right? So 1/4 is 0.25. So in the end, this is just 0.75 or 3/4. That's it. Okay? Okay, now let me show you how you could do this using R. So just to remind you that we are doing this one, probability that y is less than 0.5. And remember that remember that when you use a hashtag at the beginning of a line in R, that's just a comment, and R will ignore what you typed. Okay. So first, let me define a function, and I'll call it f. It's going to be a function of y, and in this case, the PDF that we want to integrate is just 2 times 1 minus y, right? So let me write that down like this: 2 times 1 minus 1 times y. Okay? That's what I want. And then I use the function integrate. I want to integrate that function f. The lower limit will be 0, remember, 0. And the upper limit will be 0.5. Let's see, 0.75. Same as what we got by hand, right? Okay. Finally, as I said, remember we have already shown that the mean for the beta distribution is alpha divided by alpha plus beta, right? And we also have a similar formula for the variance, right? And you can derive that later on your own. It should be easy. So just plugging in, right? Alpha equals 1, beta equals 2, 1 divided by 3, that's expected value, and then just doing the same for the formula for the variance, you get variance first, then you take the square root, and that's the standard deviation. Okay, let's summarize what we've done here in this video. We have introduced a new important family of probability distributions. We have talked about the beta distribution family, right? We realized that we have met members from that family before. We have talked about the uniform distribution. That's a particular case of beta distribution. We showed that the formula to find the expected value for a beta distribution is given by alpha divided by alpha plus beta, where alpha and beta are the parameters of the distribution in question. And finally, we applied what we know. We applied the model, the probabilistic model of beta distribution to solve a problem. Okay. So that's it for now. Thank you so much for watching. Please keep working hard and take care. See you next time. Bye.